Hello Chem 1B, this is Chapter 16, Lecture Video 7, and we're going to be talking about weak bases primarily in this video. So, one of the things you know, as we learned when we discussed the definitions for Bronsted-Lowry, weak bases are proton acceptors. So if you think about weak bases, just like weak acids, they are still in equilibrium, and they have equilibrium constants. So NH3 is a weak base, right? It takes a hydrogen from water, forms NH4 plus, its conjugate acid, and forms OH minus. So this is very different from an acid equilibrium. A weak acid equilibrium forms H3O plus. In weak base equilibriums, we form OH minus. Now, in a weak acid equilibrium, I generally don't show this. I almost always show it as with water, it goes to H3O plus and A minus, but you technically can write this as HA goes to H plus A minus. H3O plus and H plus are really identical substances. And we can totally write this like this or like this. We can't write that for bases. Bases have to have water in their dissociation equations. Let's think about why. When this guy gains a hydrogen, where did that hydrogen come from? It came from the water. Because of that, we can't ignore water. The base has to accept a proton from somewhere. In this case, the proton is coming from water, always, pretty much in weak base dissociations. Now, we define the equilibrium constant for weak bases as a Kb value. So Ka is for weak acids, Kb is for weak bases. Again, it's still just a regular equilibrium constant, NH4 plus over OH minus divided by NH3 in this case, or just, products over reactants. So let's talk about a problem. There's a very slight difference in weak base solutions in terms of like calculating pH than if we were to calculate pH for a weak acid solution, and that is that weak bases, their equilibriums don't produce H3O plus, they produce OH minus. So we have an extra step to our problem here. Now, for the most part, it's very similar still. We know we have 0.3 molar according to the problem, NH3. We know we don't care about H2O because it's a pure liquid. We initially don't have any products present, and we can kind of fill in our change as per usual, right? Plus X on the product side, minus X on the reactant side. Our equilibrium rows are just the sum of the two, initial and change, and we get all this. Now we can set this all equal to our Kb value, again, products over reactants. I am going to use the 5% rule here, right? If we use the 5% rule, this simplifies the problem significantly. We can multiply both sides by 0.3 to get x squared is equal to 5.4 times 10 to the negative 6. And then square root both sides to get x, which is 2.3 times 10 to the negative 3. Now, that's all great. It's very important to recognize that this x value is not equal to H3O plus. It's equal to the OH minus concentration according to our ICE table. So if you take the negative log of this value, you have not calculated pH. You've calculated pOH. And this is the major difference between weak base solutions versus weak acid solutions. So if I take the negative log of that, that'll get me the pOH. And that's not a bad number to have. We actually probably want that number because I know once I have the pOH, which is this, I know that pKw, right, is equal to pH plus pOH, or in other words, 14 is equal to pH plus pOH. So if I have this guy, then I can solve using this equation for pH, right? So I know that pH is equal to 14 minus pOH, and here I do have my pH of my solution. Now, if you forget to do this last step, if you just spend 2 seconds looking at your answer, you'll really quickly realize this can't be the pH of the solution because we added a weak base. And if this was the pH, that would be the pH of an acidic solution. Adding a base is not going to make an acidic solution. It's going to make a basic solution, which means the pH has got to be above 7. And if we subtract from 14, we get that. We get 11.37 as our pH. So let's do another example here. What is the pH of a 0.654 molar solution of methylamine? I'm giving you the formula here. We should be able to write out an equilibrium expression and all that if I give you the formula. If I don't give you the formula, call it A-. That's totally fine too. But if you're given the formula, you should be able to write it out. So let's say we have CH3, NH2. All right, this is our weak base. We're going to react it with water. It goes to form CH3 NH3 plus OH minus. We have a Kb here that is 5.0 times 10 to the negative 4. And we can write out a nice table. All right, we have 0.654 molar initially of this guy. Really don't care about water. Our initials for our products is going to be 0. Our change is going to be minus x, 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 and 0.654 minus x. We can set this all equal to our Kb. 5.0 times 10 to the negative 4 is going to be equal to x squared all over 0.654 minus x. I'm going to use that 5% rule here, get rid of that, and solve for x. And if I do that, I get that x is equal to 0.0181 molar. Now we do need to check to make sure the 5% rule here is valid. So 0.05 times 0.654 gives me 0.03. We're way below that, so we're good. The 5% rule worked. Here is my x value. Now I'm asked for pH. This is not equal to the H3O plus concentration. That's not at all true. What it is equal to is the OH minus concentration, as we can see from our ice table what x is equal to. So if I take the negative log of my concentration here, 0.0181 molar, I'm going to get my POH, which in this case is equal to 1.74. Now I'm not done. That's not my pH. That's my POH. And so pH is going to be equal to, like in the last problem, 14 minus POH, which gets me 12.26. This makes sense because it's a basic pH. We have a basic solution. Yeah. So if you have any questions, let me know. Let's talk about one last topic before we move on. And so there is actually a relationship between Ka and Kb, but it's got to be for a conjugate pair, right? So like for instance, HC2H3O2 and C2H3O2. These are a conjugate pair. Here's the weak acid, here's its conjugate base, or here's a weak base, here's its conjugate acid. The Ka for this has a relationship with the Kb for this. We need to know what that relationship is. For a conjugate pair, or for NH4 and NH3, any conjugate pair, Kw is equal to Ka times Kb. And I'll proof this in a second from theory and why this is the case. But you do need to be able to use this equation. If I know Kb of NH3, I can solve for the Ka of NH4 or vice versa, which is super useful. Kw we know is 1 times 10 to the negative 14. And what the consequences of this equation is, as this one goes down, this one must go up, because this is always equal to 1 times 10 to the negative 14. So as you get a stronger acid, you get a weaker conjugate base, or vice versa. So the larger the Ka, the smaller the Kb of its conjugate will be. We can take the negative log of both sides of this equation here, and that gets us that pKw is equal to pKa plus pKb, or in other words, pKa plus pKb is equal to 14. Again, this one only works at 25 degrees Celsius, because that's the temperature that Kw is 1 times 10 to the negative 14 at. But this equation works at any temperature as long as you know Kw at that temperature. So let's see why this all works out. Why does multiplying Ka times Kb give you Kw for a conjugate pair? Well, let's look at the equations, right? This guy is the weak acid dissociation of NH4. This is a Ka, we're forming H3O+. The weak base dissociation for NH3 is this equation. We know that's a Kb because of the OH-. If I add these two together, notice what happens here. The H2O adds together. The NH3 here cancels with the NH3 there. The NH4 plus cancels with the NH4 plus there. And what we're left with is H2O plus H2O on the reactant side, and H3O plus OH- on the product side. So if we add these two equations together, we get this equation. If you don't remember, this is the equation for Kw, which means, what's our rule for adding two equilibriums? Well, we learned that back in chapter 15. When we add two equilibriums, we multiply their equilibrium constants together, and that's why this whole equation works out. Now, since I know the Kb of NH3, if I wanted to know the Ka of NH4+, I would just utilize my equation here, plug in. Kw is 1 times 10 to the negative 14. Kb I was given here is 1.8 times 10 to the negative 5. Divide, I get my Ka is 5.6 times 10 to the negative 10. And so a very, very small number. In this case, NH3 is a much stronger base than it is than NH4 plus is an acid. But yeah. So if you have any questions, please let me know via discussion sessions or email. And this is the end of this lecture video.